Okay, so for this class, we're gonna talk about the rotation case. So last one, we talked about the vibration case, right? So for the vibration case, we just assume we have a particle is confined in a symmetric harmonic oscillator potential well, right? So for the rotation case, it would be a little bit different. And also, rotation case is more towards the practical case we're going to deal with, right? Because again, right, we are concerned about the electron behaviors. And we know for electrons in the atom, the electron is actually circling around the nuclear, right? So in that case, we're actually dealing with a case which is similar to the rotation. Again, right, in the atom case, right, it's still way more complicated now for us to solve. So we want to actually simplify, right, the situation. So the simplest case for the rotation definitely is, right, we have a particle is circling around in the plane. So it's a two-dimensional case. And two-dimensional case, what is, since it's circling, right, we're gonna just do a particle confined in the ring. So for particle confined in the ring, if we want to just show that in the Cartesian coordinates, right, you'll find the particle only appears on the circle. And again, right, if one to kind of express its behavior, I think a Cartesian system is kind of hard, right? And generally speaking, if we have the circle, we definitely want to describe this kind of behavior in the cylindrical coordinates rather than the Cartesian coordinates, right? In the two-dimension case. For the cylindrical coordinates, right, usually we just have a r and we have the rotation angle phi. So remember, right, we can actually make convergence between Cartesian system and the cylindrical, right, coordinate system. What we're gonna do is we know the x is equal to r times cosine phi, and y is equal to r times sine phi. And by simply using, right, this relations, we can always make convergence, right, between the Cartesian system and the cylindrical system. And the three-dimension case, right, would be very similar. Anyway, again, right, if we just assume we have a particle confined in a ring, we want to know how the particle gonna behave. So we're gonna, right, look at, or we're gonna solve the Schrodinger equation, right? We want to know the wave function. And let's just assume, right, there's no potential energy. Again, this kind of assumption is not practical because we know if we don't have an object doing this kind of orbiting behaviors, we definitely need a force, right, which is pointing to the center. But again, right, if we add that force, we're going to introduce a term, right, a potential term. They're going to complicate our calculations. And we always want to start from the simpler case. So let's just assume there's no potential energy. The particle just confined in this two-dimensional ring. Still, right, in the Cartesian system, we can write down the Hamiltonian. Since there's only kinetic energy, so we only have kinetic energy operator. In the Cartesian system, we have the x direction component and the y direction component here. And if we're gonna expand that into the right operators, we have the minus h bar squared divided by 2m and times the partial double derivative on each direction. And again, we want to convert this, right, into the cylindrical coordinates, right? So in the cylindrical coordinates, what we're going to do is to convert this. And this is gonna be very tedious, right? What we're gonna do is just plug in or apply this x equal to r times cosine phi and y equals to r times sine phi to express them, right, with r and phi. Since it's very tedious and takes time, I mean, it's solvable, but it really takes time. I will just give you the final answers here, right? Once we do the conversion, you'll find it becomes like this, plus 1 over r squared. And again, it looks complicated, but we can actually further simplify this expression. Because we know, right, since it's confined in a ring, the r is actually a fixed value. So that means, right, any derivative against r should be 0, or even, right, double derivative. So in that case, alpha against derivative r should be 0. Double derivative against r should also be 0. So that means this can be actually expressed as just 1 over r squared. And we have the partial derivative, right, which is double 1, right, against the angle, the phi. And again, right, since now we only have one variables, we don't need this double derivative symbol, right? It becomes 1 over r squared. Normal derivative against the angle. So from here, what I can do is we just plug this, right, to replace this. So now we can write down the Hamiltonian actually equals to minus h bar squared divided by 2m. In the Cartesian system, and that actually equals to minus h bar squared 2m, and we have the 1 over r squared, and we have the double derivative against the rotation angle. Again, if you look at here, the mr squared, if you still remember your physics, right, the mr squared in the rotation is actually equals to the I, which is the moment of inertia. So in that case, right, the Hamiltonian or the energy operator can be equal to minus h bar squared divided by 2I. And you have the double derivative. So here we can actually write down the actual Schrodinger equation. So the Schrodinger equation is gonna be, right, the operator applies on the wave function equals to the energy times, or the eigenenergy times the wave function. And let's just expand it, right? Now we have minus h bar squared divided by 2I. We have the derivative, right, against this wave function. And we have this. And again, this is hard to solve. But if we just observe this expression, you'll find this term, right, minus h bar squared divided by 2r, it should be a constant. And E is also a constant. So now you will find, right, this expression is very similar, right? Very, very similar to what is like, right, for the free energy, for the free particle case, right? So what we're gonna do here is actually to say, right, if we have h bar squared divided by 2r square rooted equals to ml, right? Then we'll have this case that is I ml squared and you have double derivative. Sorry. You will have this double derivative equals to e times phi, right? This expression. And apparently, right, similar to free particle case, right? We know that this wave function should be proportional to e to I ml times phi. Right, that's what we have learned. And remember, if we do the same treatment, right, we can write down the full expression. This wave function should be a times e I ml phi plus b times e minus I ml phi. And again, right, since it's a circling behavior, right, remember we have this circling behavior. So no matter how it circles, it always goes back to, right, the original stage. So we don't really need a and b terms, right? They are the same. So what we're going to do is just simply equals to a I ml phi. This is enough to actually, right, to express this wave function. So now we actually have this expression of the wave function. What we need to do is actually to find out what ml is and what a is, right? So remember, right, once we have the wave function, what we're going to do next is to apply the boundary conditions. And we know, right, at the boundary for the wave function should be continuous. The continuity of the wave function means, right, at the boundary, two wave functions should be each to each other. And here we only have one wave functions. What is the boundary conditions, right? Another boundary condition is the derivative, right? On both sides equal to each other. But here, it's a circle, how we can apply the boundary conditions. And you'll find it's actually pretty simple, right? Since it's a circle, right? So that means every time you complete the circle for the wave function has to go back to the original stage, right? So in that case, we call that a cyclic boundary condition. That means that you have the phi. Every time you finish the circle, right, this wave function will be unchanged, will be the same. This is the wave function, right? So then what we're going to do is just plug in, right? So here we have the a times e I ml phi plus 2 pi equals to a e I ml phi. So again, what we can do is to cancel out the a, and here what we can express is e I ml phi times e I 2 pi equals to e I ml phi. Again, this part e I ml phi can be cancelled out, right? So that left us e I 2 pi. Oh, I'm sorry. Here we still have the ml, right? e I ml 2 pi. So here we have the e ml 2 pi equals to 1. Here we're going to play a little bit trick, right? We're going to express this into e times I 2 pi power ml equals to 1. And by using Euler's law, right, e I 2 pi equals to what? Cosine 2 pi minus I sine 2 pi. So what is the cosine 2 pi? Cosine 2 pi, if we just draw the cosine function, right, this is 2 pi. This is actually 1. And for the sine 2 pi, if we draw the wave function, right? This is a 2 pi. This is 0. So it's 1 minus 0 equals to 1. So that means 1 times power ml should be equal to 1. And the ml, right, needs to be a integer. Now we solve the ml, right? And the integer means we can be 0, 1, 2, 3, 4. Or even -1, -2, -3, -4, right? And what we find is this ml is quantized. And remember, the ml equals to what? ml actually equals to square root h bar divided by 2i. Since h bar is a constant, right? The ml is quantized actually means, right, the momentum, the moment of inertia, the I is quantized. And in this case, we're going to name ml, right, as a quantum number, right? ml, what we call is actually called magnetic quantum number. So why we call that magnetic quantum number? The reason behind that is because, right, if we think about the moment inertia, right, we use our left hand or right hand rule, right, we find, right, you always has the, right, your thumb pointing, right, perpendicular to the circling of things, right? And remember, normally we deal with electrons, right? If we have a circling electron, it's gonna generate, right, the magnetic moment. So in that case, right, we just say, right, this probably is related to the magnetic properties, right? So it's called the magnetic quantum number. Okay, so now we actually know what the ml is, right? If we write down the wave function again, we know that's equal to a times e to I ml, the angle, and we know ml is integer. Let's do one part we did not solve, right? The a. So now how can we solve the a? Again, right, just record what we have learned, right? We're gonna do normalizations. How can we do the normalization? We're gonna utilize the weight, right? The integral of the probability density in certain region should be equal to 1, right? In this case, it's a whole circle, right? If we integrate the whole circle, remember we have this circle, right? Whole circle should be equal to 1, right? The probability should be equal to 1 because the electron is, right, is confined in this circle. And now what we can do is just do the math, right? So the conjugate products of this wave function is simply a times e minus I ml phi, and times itself e I ml phi. We have the d phi equals to 1. And from here, what we get is you have the a squared ei ml phi times ei minus im phi, right, is equal to 1. So we have the integration 1 d phi equals to 1. And here it becomes 2 pi a squared equals to 1. So the a is equal to 1 over 2 pi. So in that case, we have the expression, right, of the particle confined in the ring. Which is, let me just make it important, right? You get the expression equals to 1 over square root 2 pi e to I ml phi. And this is the expression. And now we know the wave function. The next step is to find the eigenvalue, right? The eigenenergy in this case. So what we're going to do is to put this wave function back to the Schrodinger equation. So remember, we have our Schrodinger equation. Like this, and we just plug in that, right? So again, the Hamiltonian we have learned is minus h bar divided by 2m, and we have the double derivative d phi square and we have to express the wave function is this 1 over square root 2 pi times e I m l phi, right? Equals to e times e I m l phi. And let's work on that. We have the minus h bar squared 2m, and we're gonna do double derivative, right? So it's 1 over 2 pi. The single derivative is IML, right? Double derivative is actually IML squared. And you have EIML phi equals to E to IML phi. And you find this EIML phi, right, can be canceled out. So that then we will just have the energy equal to what? To, in that case, to 1 over square root 2 pi minus sign times h bar squared divided by 2m, and I here, right, I squared is minus 1 times minus 1 times ml squared equals to, there's no equal, right, just equal to this part. So in that case, right, we can actually get the energy. So in that case, right, let's look at them. So will be equal to, let's write all of them down. That's equal to, let's do a little bit expression. So what we're gonna do is, in that case, we have the we have this minus 1 minus be cancelled out, and we have the h bar squared 2m times square root 2 pi equals to times ml squared. That's the expression. And again, we can do a little bit expressions here, because if we look at the 2m, the m times the square root 2 pi, it's actually equal to what? Square root 2m squared pi. This can also be equal to the momentum of initial. Oh, sorry. I think I got something wrong here. Yeah. This is not m, right? This is I. So now what we're gonna change is I is here. So we're gonna change also I here. So in that case, right, we actually have h bar squared 2I square root 2 pi oh sorry, I'm sorry again. So again, here, this is not, the wave function is not here, right? The wave function here is actually 1 over square root 2 pi, right? E2 IML phi. I'm sorry about that, but yeah, I just plug in the wrong expression, right? It's 2 pi E IML phi. So again, what we can do is to cancel out both, right? So then things gonna become like much simpler. I'm sorry about that, but I think we're gonna make it work. E will become to minus h squared divided by 2I, and you have the I squared is times minus 1, you have the mi squared. So in that case, right, you will find the energy actually equals to ml squared h bar squared divided by 2I. Right, this is the expression of the energy. Again, you need to remember that, right? So you find, right, since momentum is, right, since ml is quantized, that means the energy is also quantized. Okay, so here, what we're gonna do is to introduce another thing, right? The angular momentum. Remember, right, if we have the circling thing, usually we have a circling, right? We always can introduce the angular momentum that's equal to the momentum times the r here, right? The radius here. I believe you definitely have learned that in the physics. So it always has a z direction of the angular momentum that's actually equals to the vector momentum times the radius vector, right? And in the Cartesian coordinates, it becomes x py minus y px. And if we look at the angular momentum operator, right, it's actually equals to h divided by I. So we have x partial derivative and equals to h bar divided by I d phi equals to minus IH derivative d phi. So if we use this angular momentum, right, operator applies the wave function we just got, you'll find that's equal to 1 over square root 2 pi times IH bar, and you have the IML EIML phi. That's equal to 1 divided by square root 2 pi times ML H bar E2 IML phi. So it's actually equal to ML H bar phi omega phi. And you'll find, right, this angular momentum operator can all applies on the on this eigen wave function for the energy, also gives you a eigenvalue, right? This is the real value. So that means, right, the angular momentum is also an eigenvalue, right? Is eigenvalue for the Schrodinger equation, for the energy eigenfunction, right? So sometimes, right, we're gonna use this angular momentum. And again, right, the angular momentum L here actually equals to ml h bar. It's also quantized. And that's what you need to know for the particle in a ring.